So yeah, thank you for the introduction. Like Robert said, I started out over in the interdisciplinary program and then took a hydro class and fell in love with it, but still wanted to get my restoration certificate. I think it's been a great, it's a great pair. So, and actually I first got interested in beaver restoration at attending a couple of restoration seminars that talked about using beaver in restoration. So that's kind of what sparked this. And this is my beautiful site. I was up here in the summer. So this is where we're going to be for the next 40 minutes or so. You can see the beaver dam right here. Hopefully, I turned my pointer big and bright purple, so hopefully you can see it. The beaver dam right there. We're in Muddy Gulch up in the Anaconda Highlands. So a lot of us know, and some of us don't maybe, that beaver is a big hot topic. I don't expect you to be able to read the text on here. I just thought this was a really great graphic, and this Dr. Emily Fairfax out of CSU did this, and it just highlights some of the benefits that beaver naturally bring to the landscape, and as they've been trapped out, we've lost some of those benefits. So there's a lot of investigation into what natural beaver dams do, and beaver dam analogs have become a very hot topic, a very popular restoration technique, rightfully so. Beaver are a keystone species because they provide several important ecological services, including habitat formation, wetland creation, and they maintain wetlands as well. Revegetation after fire or any kind of land destructive activity. Sediment capture, so it holds sediments back and prevents sediment loading into creeks during flood events, which is very beneficial to fish. Water storage and groundwater recharge. So down here in the corner, if you can see that, you see when you hold water further back up in the watershed, it has a chance to filter in and raise up that water table. We also get hydrograph attenuation, which means during big flood events, we don't get these really flashy hydrographs. We get a much more even flow of water down through the system, which helps prevent erosion and helps prevent creeks from aggrading. So aggrading creeks are when it goes down and it can't overbank flood into the riparian area, and you don't get that nice marshy, mucky stuff. So beaver can also help bring those creeks back up. It can aggade them from being incised. So those are just a really brief overview. That's sort of what I found a lot of in the literature. A lot of literature talks about sediment capture and improving water quality in that way. But my curiosity was, what types of sediment are retained in the beaver dams? Not just how much, but what type, and can it affect water quality in any way? Is there any benefit to water quality from all the sediment that these beaver dam complexes can hold back? So that was sort of what sparked my curiosity. And I stayed afterwards, after a lecture one time, and talked with a great group of folks. And Pedro Marquez from the Big Hull Watershed Committee offered up a site. They were planning restoration in the area, and he said, hey, if you want to come drill some cores and analyze them and see what's going on with the sediment, have at it. So he gave me the green light, gave me the contact for his excavation company that he works with. I found a driller and we went for it. And I really have to give props to Pedro for just giving me that green light and sort of letting me be involved in some of the planning. He did a lot of the back end work, but I did a lot of the coordination. And that was really great learning experience for me. So my goals then for this project were to provide data about contaminant attenuation and nutrient retention in a natural beaver dam system. This data was then used by the Big Hull Watershed Committee to inform their restoration plan. They really wanted to know whether or not to dig or not to dig was the question in this area, and were the unfavorable soils sequestered enough to allow vegetation recovery, or did they need to dredge it out as part of their restoration? The second really applied goal that I had was to design a reproducible field-based process. So I was really looking for sort of a methodological outline for future work. I wanted to be able to provide something that would give real-time data in the field that we could use. So those were my goals. So those were practical goals, and also trying to satisfy that curiosity, because I have an ever curious brain. We are located here in Montana, and we can zoom in a little bit and see that we're just west of Butte and just south of Anaconda. We're going to look a little bit more at that. This is a little web app that I created, just sort of starting to mess around with web apps. But Butte, again, Anaconda, and this is the entire Mount Hagen Wildlife Management Area. It's over 56,000 acres with several different drainages. You can see the different drainages here, and we're down here in Muddy Gulch. So I'm going to zoom in a little bit more. And right up here on the edge, those dots are where we drilled some sediment cores. I am going to flick on a layer over here. Don't worry about seeing all that. I'm just using it to kind of control. And you can see very steep erosive gullies up in here. The site itself is about 6,000 foot elevation, and we're semi-arid. So some of this barren hillside that you see is natural, and some of it's not. A lot of this was deforested in support of logging and mining and to fuel smelters and a lot of mining related infrastructure. You can see right here a really big log flume. It's very evident on the ground. And so big erosive events in this area, lots of contaminants washing off the hillside because it's also been impacted by smelter emissions. There have been reseeding efforts on the hillsides, and the Big Hull Watershed's doing a lot of great work up there. So zooming in a little bit more, this is my pond. Got very familiar with this great place, and for now, I just want you to get familiar with the cores. So we have the downstream core, the mid-down, mid-up, and upstream. So we drilled these cores on a linear gradient from upstream to downstream. We're going to be talking a lot about those 4 cores, so I just want you to know the names. Here's a little bit better site layout for you to look at. So here's the top of the historic Beaver Dam, and over here on the side I have pictures of that. It's pretty long, 476 feet. The dam breached sometime into 2012 or 2013, so it's been dry. This dry pond surface where we drilled the cores has been dry for about 7 to 8 years, and since then the creek has incised. Here's the breach over here. The dry pond surface where we drilled the cores, and the incised creek. The depth to water on this dry pond surface is 5 to 7 feet, so it's been sitting high and dry for a while. The Beaver Lodge over here, it's a lot bigger than it looks. I didn't get super great measurements on it, but it was really cool to see that. You could still see where they used to dive in to their little home. So methods. The way that this went about was, the very first thing to do was to drill cores. The excavator came out, he had to clear out a few willows, make a little, fill in a couple little trenches here so the drill rig could get out. R&S Johnson Construction, some really skilled guys. It was great to work with them. And then James Rose from the Montana Bureau of Mines and Geology came out with his GeoProbe truck, and we drilled 4 cores in just one day. They're little guys in 4-foot sections, and they come out in these PVC tubes. So I was able to sort of roughly log them and then cap them to transport them back to the lab. I didn't cut them open in the field because I would be doing chemical analysis on them later. And then back in the lab, so my little lab helper, my daughter Addie, and she helped me measure percent recovery. And then I moved the samples to refrigeration as I was awaiting the nitrate meter shipment. Once the nitrate meter showed up, I was ready to cut open the cores. I didn't use a set interval. Instead, I I identified areas of interest, and those are areas where the sediment texture or color changed, where there was biotic debris, where water content changed, or where iron staining or copper oxidation was readily visible. So this is my process here. Specialty geoprobe equipment to slice open the cores. I had almost 20 of these, had 19 of these cores to slice open, identifying areas of interest and marking it on the core, labeling the containers, and then scooping out with a non-reactive tool and washing and triple rinsing with DI water between each one to prevent cross-contamination. Testing for nitrate and nitrites. I use two methods, nitrate quick test, which is commonly used in agriculture. I used a 1-to-1 soil to water ratio with water leachate and dipped water quality strips in. And the second method was a Horiba scientific meter just for nitrate. It used the same leachate water. And of course, I did set up and calibrate that meter before I started. pH analysis. This one, I used the previously prepared samples, but I had to dilute it to a 1-to-2 soil water ratio. That's just standard best practice for the pH meter. I did a 3-point calibration, and the meter was recalibrated every 15th sample. It's that little handheld guy. And I took QA/QC readings to make sure the meter stayed reliable. And then to test for heavy metals, I used a handheld XRF analyzer. This is a close-up of the cores, very heterogeneous, wide variety of material, and I just thought this was gorgeous. It was fun to work with. So the XRF analysis was very safe with the gun that shoots X-rays, but in reality, I did get an SOP from Steve McGrath at the Bureau, and I did get training on safety from the lab and also from Dr. Chris Gammons, who's over in the geoscience department. He's the XRF guru. So, and he also helped me figure out how to configure and set up the gun so I could get the readings that I wanted. Went through a system check and shot standards every day before I started. This is not something I can calibrate myself, but the Bureau does calibrate this regularly. So I just did a little check every day to make sure that it was working properly. The scan range that I did, I adjusted it a little bit. You see, I went to a higher scan range, and that was just to reduce uncertainty. I was getting a high uncertainty value when I first started and just wanted to make sure I got the best data possible for these elements that I was looking for. And so I adjusted methods as needed as I went along. And then to prep the surface, so this is a real close-up of the cores. Ideally, an XRF sample is homogenized and in sample cups, and the XRF gun itself rests in a stand. But I was really looking for a field-based method, and so I kind of went for a middle road. I treated the cores as if they were in situ measurements, and this is commonly done. In situ measurements are commonly taken in industry. So I just leveled the surface, looked for a place that was fairly well sorted, not too big gravel. I leveled it and then covered it with a little bit of plastic wrap to protect from cross-contamination. And then I shot each of the 71 sites with an XRF gun. I rested it level on the surface. And talked with some people about diffraction and didn't think that that was going to be an issue with the level, with it resting on there. I did also take a quick water quality sample. I took this at base flow in August because that's most likely the time that you'd see anything is when you have the least amount of water kind of trickling through the system. I did one at the inlet of the pond and one at the outlet, and with help from my committee member Jackie Timmer, we filtered and preserved per her lab requirements, kept on ice, and got those submitted in time for within holding times. I also had a great day in the field with Dr. Tom Keck. He's a soil scientist based out of Bozeman, and he taught me a lot. And I was very grateful for him sharing his expertise. We did a hike of the area. We hand augured a hole. I learned about soil color typing, soil color classification, and we also dug a horizon in the side of the Beaver Dam to sort of see some of the layers. So some of my results, before we get too far into the weeds with results, I should say that I analyzed all this data that I was collecting based on, I don't expect you to read all this. This is just a snapshot of the sheet, the page that I pulled out of the EPA's record of decision. So as part of the ROD process, they did an ecological risk assessment specifically for this wildlife management area in the Anaconda region. And so I was able to use these parameters. This is what they would like to see post-restoration. And so I was able to use these criteria to evaluate the pre-restoration conditions. And I focused mainly on items 3, 4, and 5, which were texture of the soil, pH, which they wanted to see between 6.5 and 8.5, and then limits for metals concentrations. So as we go through, any kind of comparisons I do are going to be based on this reclamation criteria. So what did I have to work with? I had these beautiful cores that James Rose drilled for me, and we had planned all the cores to get down to 20 feet. The most upstream one, we encountered very hard drilling at around 16 feet and couldn't progress the 16 to 20 foot segment. So that last one wound up a little bit more shallow. Got good percent recovery. It ranged from 50 to 65%, and that is considered a representative sample when using the sampling technique. Lack of recovery is usually due to a small pebble or maybe it's some real thick clay that can plug that drill pipe shoe. But like I said, 50% or more is considered representative of what's there. I was a little nervous about that number. It didn't sound like enough. So lucky for me, I had a couple of opportunities to sort of truth that, and the geoprobe does a great job. So one of the big findings was this clay lens down at 3 feet below surface. And the day that I went out with Tom Keck, we found that clay lens in that hand augured hole. So the knife there is indicating that. These real high chroma soils too show that the deposition's been fairly recent, within 50 years, and groundwater is not persistent at those depths, which is another thing that I saw on the cores, was not a lot of wet until further down. Also saw interspersed layers of sand with finer sediments, which really shows that there's these big wash-in events to the pond with some settling out, large erosive events. Another great opportunity to field truth was when the big Hull Watershed came in this fall and actually did their restoration work in the area. The excavators, again, the guys were great. They let me get in the way and dig out some samples, and I was able to verify what I found in the mud logging, and the cores were just, again, right on. This is a sediment facies cut that I was able to make, and it was about 6.5 feet high, which was great because that's where I saw most of the compaction in the cores. So I was able to see again at sites 3 and 4 over here. Here's the close-up clay lens, and also these striations up here are actually ripple marks. So that shows the water coming in and also the direction of flow into the pond. So that kind of confirmed our thoughts about where the water was initially entering the pond before the creek incised. So that was great to see. Another really exciting thing to see on this day was this I suspected that I found an original soil horizon in the cores, and I did in fact see that at about 5 feet underground. So that would have been before the beaver came in and plugged it up. So here's this original soil horizon at about 5 feet underground. And that's down here at sites 6 and 7. So it's really great to have that confirmation. Nitrate and nitrite results, they were undetectable using the nitrate quick test, and values from the meter I actually threw out. You can see over here it was pretty unreliable, and I think that's because we were out of the range that I was able to calibrate the meter to. Nitrates, these test results show that nitrate really was the limiting nutrient in the area. So we know that it is limiting nutrient up on the hillsides where there's been a lot of topsoil erosion, and it is also the limiting nutrient down in the valley bottoms, even where all that topsoil is collecting. So that was good information, I think, for the restoration, because they knew then that they were going to have to include nitrate fertilizer for sure in their restoration design. And pH. So we're gonna start looking at some depth profile graphs now. The way to read these is at ground surface, right up here is 0, and then we're going down below to the total depth of the borehole. So it's as if you were standing and being able to look at the soil underground. These points here are my actual data points, and the lines, it's not continuous data, the lines are there in between the points just to help illustrate those trends. So you can see here the pH, the lowest pH is 6.08. This one wasn't too bad. In red here did not meet criteria, and green did. So we're not too far below that 6.5 cutoff in the upstream core. In the mid-up core, we were a little bit lower, 5.52, but still a lot that was in that criteria range. In the mid-down core, this was the one that had the lowest pH, 4.75, getting a little too acidic for plants at that point. And again, the EPA would like to see a 6.5 to 8.5. The downstream core had quite a bit below criteria, and again, getting pretty low there at 4.77. The upstream core, we're going to come back to that later. So now these are depth profile graphs. This is a composite graph of what's considered locally the big 5 heavy metals. So these are the most commonly seen and most concerning contaminants in this local region as a result of historic mining and smelting activities. So this is a composite. We have lead, arsenic, zinc, copper, and cadmium on this graph. And I don't want you to worry too much about the values at the bottom here, and just sort of pay attention to the trends. So you can see right here, we sort of have a trend here at about 7 feet underground. In the mid-up core, we have a very strong trend at about 3 feet underground, and this was the highest values that we saw in any of the cores. In the mid-down core, another trend right there around 4 feet. And in the downstream core, pretty recognizable trend at about 7 feet. So those are where the metals were kind of all spiking in one layer. But what does that mean compared to the EPA criteria? Well, there were exceedances. So in green, we have, I should set this up for you, sorry. We have the elements over here, the EPA criteria, the upstream cores, and then you can read down to see each element in each core. And this is the highest value per element in each core, regardless of depth. In green, it meets the EPA criteria, and in yellow does not meet the EPA criteria. Orange also doesn't meet and is also the highest overall value. So we had quite a few exceedances in this pre-restoration sediment. The mid-up core, you can see the values just seem out of sight. They were really high. I questioned it. Big Hull Watershed questioned it. NRDP questioned. Everybody questioned this, rightfully so. We put this under a lot of scrutiny. I retested it again in May, and you'll see another retest here for that core, that site and that core in October. And that was because when I went out on excavation day and shot some in situ values last fall, these values were fairly close to what I saw in all the other cores, but again, didn't see anything nearly as high as what we saw in that mid-up core. So I went back for the third time and tested that mid-up core again, just to triple check. I also kind of took that core apart, just destroyed it. I was looking for a foreign object, a rock, a piece of metal, something that would explain these high values. Didn't find anything. There was just dirt. So that's one of those, I guess every project has to have one of those mysteries, but that was a mystery. My only thing that I can maybe explain with that is a really highly localized little clay lens that was just grabbing onto all those metals, sorbing all those metals, and just really holding on to them. So that was the project mystery. In situ values, so again, on that excavation day, I shot some readings out there, and using these EPA criteria, we did have exceedances, and a lot of these higher in situ values were correlated well with what I saw in the cores. So another sort of true thing for the cores, that it really did give good information of what we actually saw on the ground. So coming back to these depth profiles, I now have them lined up correlated with the lithology, so the well logging that I did on the cores, and so sediment typing and texture. And here you'll see clay, clay, clay. There's going to be a theme here, I promise. Clay with heavy organics, and again, that was that mid-up core that we just talked about with the really high values. Clay again, and surprise, surprise, clay, 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 and organics. So what does that mean? Why are these values spiking in certain areas? Why is it always clay? There are reasons, I promise. This was something I learned from Glenn. There are a couple different types of sorption that are likely happening here. There's sorption via cation exchange. And so in a sandy sediment, these, I should say, sorry, the elements of interest that I was looking at, arsenic, cadmium, copper, lead, and zinc, they all typically carry positive charges. Arsenic's kind of a funny one, but in aqueous systems, we do see it with a +3 or a +5. So they will just filter through most sediments, but clays are unique because they have a negatively charged surface. Let's not get my right and left mixed up here. Clays have a negatively charged surface, and they are going to attract those positively charged metals as they move through the system, which is good news for the water filtering through. Not so great news for the sediment that's left behind, but it does tell us that, hey, maybe these clay sediments are sorbing on, and maybe these systems can act as sort of a water filter. Another possible sorption mechanism is that a lot of elements are going to undergo a chemical reaction when they're exposed to air or water. So you think of rust or copper oxidizing, when copper turns that green color, that is one of the things that could possibly be happening here. the elements are going to bind there to that site, and it's a very strong covalent bond. They're very unlikely to desorb, and because at that point they really are incorporated into the sediment and probably won't desorb from the surface. So those are the two mechanisms that might be at play here. Would need to study that further to know exactly what's going on, but everything sort of indicates that something is sorbing in that system. One other thing that is indicative of that was the water quality results. A lot of these are within error range, but I did think it was interesting that the pH went up, the conductivity went down, and all of the values went down. Lead went from 0.5 micrograms per liter to non-reportable or under reporting limits, and zinc from 1.07 to under reporting limits. So I did think it was interesting. Even though this is not definitive, it is some suggestive evidence that this complex really is sorbing contaminants. Okay, we're gonna take a deep breath. We're through the hard part for those of you whose eyes kind of glossed over with lots of charts. I know mine do sometimes too. Now we're gonna get to the interesting stuff. So with all of that evidence, all of that data, what does it mean really? For the restoration plan, it shifted some things. This was just kind of off the cuff thing that I sent to Pedro and Ben from the Big Hull Watershed Committee. They were kind of finalizing. I think Ben and I did a Zoom meeting at one point to talk about what was going on under the surface. And so the restoration design shifted from a plug and pond approach where they would plug up the beaver dam and allow it to infill again, to more of a meandering stream with some armored step pools, some places for overbank flooding where things really were a little bit more secure during those big erosive events, and the rest of the time we just had a really good, healthy creek moving through the system. These were the final design plans from Pioneer Technical. It was super great, again, to be on the ground during excavation day, to see this design get put in process and to see how Pioneer Technical's really awesome flexibility. Like, oh, we planned this, but now that we're on the ground, we see we need to push a little further. And just the communication between the team, between Ben and Pedro and the operators, Dustin and Scott, out there excavating, and then the folks from Pioneer Technical. It was really great to be a part of that process. So again, I appreciate them letting me kind of get in the way out there. The other thing too that I really wanted to do for the Big Hull Watershed was they do so much out in the field, and I know they are big on redesigning as you go and being okay with being out there and kind of on a napkin, off the cuff redesign. And so throughout this whole process, I looked at it and said, well, how can this be a field-based process? Is this doable in a lot less time? Because I was sort of trial and error, and it took me a long time to get through all of this. And I think the question is, or the answer is yes. I think that it's very feasible to set up an assembly line type thing and get all of these analysis done in a matter of a day or two with a team, 3 or 4 people out there, and get some real-time data. You can cut open the cores on the side of the drill rig. The XRF is a handheld instrument. The pH and the nitrate meters, all that's handheld. And I think that we could do that, sketch some simple depth profile graphs, and get some real-time feedback. Save some time and money. Who doesn't want to do that as a project planner? If the original plan, for instance, was to dig out 6 feet of dirt because the pH is low, but we're able to do that analysis and say, oh, the pH is only bad for the first 2 feet. Well, you've saved yourself a lot of excavation. So that's just sort of forward thinking, what I'm thinking about how could this be applied to the field? As far as future work, these are just pictures I've taken out hiking in field camp. These abandoned beaver structures are everywhere, and I think it would be great to drill more cores, identify more of these, drill more cores on these dry surfaces, structures of different ages and different climates and different hydrologic settings, with different contaminants of concern, and also to study the sediments themselves in more detail. I think that classifying them based on their absorption capacity and just getting a better idea of what's out there and what these systems are really capable of. We got to figure out a way to drill wet ponds too. I don't know, maybe we can core down out of a boat or something. These little beavers, they used to be ubiquitous all over the continent. And I think there's a huge potential, not just in the natural systems, but in all the great work that's being done with BDAs. And I think the more we can look at natural systems, and really understand them, the better our BDA designs are going to be, our beaver dam analog designs. You know, some of them kind of shoot straight through. This one, you can see some fines getting retained there. And how do we structure these so that they do, if water quality is a goal, then how do we structure them to hold back those fines? How do we prevent failures? And what do we do about maintenance? Because beavers are constantly maintaining. These structures hold up a long time after they're gone. And so I think those are just the sorts of things that we need to be looking at as we move forward, and as BDAs continue to be a very interesting and effective restoration technique. Now I get to breathe. And does anybody have, let me pull screens up. Does anybody have questions? You can unmute yourself, or I saw some things come up in the chat.
Harley, can you hear me? I'm Rick Douglas. Can you hear me?
I can hear you.
Okay, I was a professor in the biology department for a lot longer than I'd like to admit. But I watched Joiner Gulch over almost 40 years being completely changed by beavers. And I was mostly interested in the active beaver ponds and how frequently they came and disappeared. But Rick Appelman, an environmental engineering professor, and I went up, and the creek, main creek was basic, and all we could find in it was arsenic. But then I had another student that bailed on me, of course, they always do, look at the ponds themselves, and we did some cores in the base of active ponds thinking that we would see contaminate from metals decreasing as you went up through the core. But what we found is, because of the way flooding affects beaver ponds, is that sometimes it would decrease, and next thing you know, you get a big load of it. The beaver ponds would wash out, a new one would come in. This is completely different than what you did. But I can't remember his name. In environmental engineering, and his student looked at the effect of water quality at the head end of a beaver pond and the outlet. And as I remember, this is published in the Intermountain Journal of Sciences, as the water ran in, it was kind of basic, but as it left, because of organic accumulation, it turned acidic, and that made it pick up some metal. So that's all I have. I don't have any questions for you, but if you want to go look at Joiner Gulch, get a hold of me. I've been looking at it for years.
Was that Martin Lorenzo that did that? I think I read his paper.
I think so.
Mm-hmm. Yes, very interesting. Thank you.
Okay, that's it. Good job.
Martin worked on a beaver pond off of Mill Creek near Anaconda.
Right.
And that was after you retired, Rick. That was like 2014, 2015.
So
I think you may have a different student that worked in Joyner Gulch.
No, this was, they did not do the study in Joyner Gulch. They did it in
Okay.
Cabot Gulch.
Yeah.
That Beaver Pond, I think, is gone now. They come and go. Anyway, that was my comment. It wasn't a question.
That was a really nice project, Carly. Unfortunately, the internet connection through my computer failed, and so I've been looking at it on my cell phone.
Oh no.
And that means I can't see any of the. I mean, the graphs are just sort of totally too small to see. But I was quite interested. The ones that you had be green and red, it was pH across the x-axis, or
it looked like, I think somebody just stole my screen sharing here. Who did that?
don't know, you still are sharing.
got your special thanks. You just have to go to a different slide.
Okay. So let's see, Bev, you're looking at.
It's like maybe slide number 12 or something. I couldn't see the numbers on the slides either, though I could tell you had them. I got a magnifying glass out, but that was a little bit later. Yeah, these. No,
Okay.
the ones before that. No, it was the graphs that.
Oh, the pH graphs.
Yeah, I was wondering if those were pH graphs.
Yes.
And then you just sort of had these green and the red. Is the scale range for all of them the same?
It is not. It is not the same. The scale on the x-axis is basically the range, is the limit. So the upstream core, 6 to 7. That mid-up core was 5.5 to 7.3, 4.5 to 7.5, and 4.7 to 6.7. So I guess what I was really trying to illustrate there was what was met criteria versus what didn't.
Right. And just as a suggestion, it would be really good probably to have them all on the same scale. That way one could really see, not, oh, they all go from the right edge to the left edge. That you could see that, oh, that not only is like this one, a lot of them are in the green, but they are nowhere nearly as acidic as some of the other ones. And I'm a person who hates suppressed zeros, but with a pH scale, there is no such concept as a suppressed zero. And the other thing is, the vertical the same, or are many of them, or a couple of them were not going as deep? This is one of the deeper ones, right?
So they all go from 0 to 20 feet, except for the upstream core. We only got 16 feet of core out of the upstream.
Okay.
Yeah.
But this the low pH part is that's the clay layer that was also problematic for the metals.
Oh yes, I should have mentioned that the low pH was also, it wasn't always right at that clay layer, but sometimes right below, which to me would suggest that as the water filters through, it's sort of changing the pH as it sort of moves through that contaminated layer.
Yeah, I think that relationship between the pH and the metal concentration is an important one to talk about. Thanks. Anyway, great project. A lot of work you did.
Yeah, thank you, Carly. You have also a question on the chat from Roy Covey. I think that's what I read. Do you have a timeline of logging smelting history relative to the ages of the deposited layers of sediments found in the ponds? That's
so that was one of those very complicated questions that a lot of us talked about. We talked about some sort of dating at some point. If you noticed on the XRF, the elements that I looked at more than I presented. I looked at aluminum to silica ratios, because sometimes that is a soil signature, and it can indicate, it can be indicative of some of that some of that, what do you call it? I'm a little bit brain dead at this point, sorry. That aluminum to silica ratio could be sort of a soil signature. And without, I also did, I should say, I chased down a lot of dead ends sometimes too. I did also look around for aerial photography, trying to go back even further than Google Maps, Google Time Slider could take me. And I georeferenced some aerial imagery to try to see if I could see when that beaver dam was formed. I found some old stuff from as far back as like the 1940s that we have laying around the bureau, which was really cool. But it didn't go quite that far away, so I couldn't quite figure out when the beaver dam, if I could figure out when the beaver dam was formed, I think, you know, and when it started filling in, I would have been able to get more of a timeline. But without that little piece of information, it couldn't quite there was no direct correlation that I could really make. So does that answer that question?
You got a couple of new messages. I'm just checking for you, Carly.
Hey, Carly.
Hi, Pedro.
Hi, Carly. Great work. This is awesome to see. I wanted to see if you could talk a little bit more about this process that you engaged in and being out there on site. I really loved where you landed on that, and the actual feasibility of doing some of this kind of in situ testing to move restoration forward. I think a lot of times practitioners and project managers, we get kind of bogged down in the time it will take to sort of do analysis, send to labs, wait for results, and the timing is usually something that we struggle with to get it all right, to be able to do good research as we're doing projects. I'm wondering if you could talk a little bit more about that piece and what you see moving forward as a potential follow-on project, to put together kind of a little guide on how to go about doing this. I think there's a lot of potential there.
Yeah, so in my paper, I did a 10-step process, didn't quite have 12, but we got the 10-step process there. And I think, honestly, with a team of people and a nice big wall tent, you could do this same analysis in a couple of days. So, I mean, really, you could cut open the cores, you log them, you record your percent recovery, you take out your samples for destructive sampling, and maybe you take out a few, maybe you can drill 2 cores side by side. So one for destruction, one for truthing, but you could take it out. And I just envision this sort of assembly line, like a wall tent with tables, and everybody's got their little stations. And so you're scooping out, and one scoop goes over here to the nitrate, and then you go over to the pH, and then the rest of the scoop gets dried out real quick. You could have a little portable dryer, because samples should be dry with the XRF gun, ideally. So you could have, a little portable generator, dry it out, shoot it, zap it with the XRF gun, and then you've got pH, nitrate, and XRF right there in the field. None of these things it doesn't take super long. It took a long time for me as one person with 71 samples, but you might not necessarily need 71 if you're just looking at the top 6 feet or whatever the excavation is going to be. I went down to 20 feet. So I think it's very doable that, hey, we started excavation, we've encountered some things we didn't think we would, or hey, we're going to go out next week and start digging this up, or even, as part of the planning process, even way before. I think it could happen. I know it took me a long time, because I was sort of trial and error as I went, but I don't see any reason that this couldn't happen pretty quick in the field. The only thing that you can't really do in the field, you can get basic water quality parameters for the water, but that does have to get sent out to a lab. So you can get pH and specific conductivity, which can give you some indication of, you know, metals. But yeah, does that answer your question, Pedro?
Yeah, totally. Yeah, it's totally relevant and a great, I think, very, I'm always looking for applied, you know, things that really apply directly, that connect the research to the field. And that's awesome. Great work, Carly. It's so awesome to have you out there with us.
Good. Thank you for having me. It's a great experience.
Any more questions on the Zoom or, I mean, my students just left the class because it's 4:56 now and the class is over at 4:50. But if there is questions on Zoom, I highly encourage to talk to Carly now.
Okay, this is Rick Douglas again. I have one comment that I left out. Can you hear me?
I can hear you.
Okay. Another student in the mining department looked at Joiner Gulch, the whole drainage, got the precipitation and used a model that mining companies use to design the size of their check dams to keep erosion from washing out. And then she went through with the available data, and I can't remember what she had. She actually went up there and measured the dams, I think, in place, and calculated there was more Beaver Pond check dam than was necessary to keep the nasties from washing out of the headwaters. And I think that's really important for reclamation. And I'm not sure, but the natural resource damage person I was working with told me they were going to build a great big check dam at the mouth of Joiner Gulch. And at the time I think he retired, they figured there was no point in it. The beavers had already done it for him. And you don't have to pay him to maintain it.
Mm-hmm.
So good job, kid.
Thank you.
Yes, fantastic job. I think we should give an applause to Carly. If you can unmute yourself, just do it. If not, just send your little messages. Thank you so much, Carly.